Next, we're going to cover a result called L'Hopital's rule. So right here, L'Hopital, L'Hopital. There is one of these symbols on top of the O. I don't know what that symbol's called. If you read the directions on, if you read the directions on the test or a few of the homework assignments, some of the questions said you may not use L'Hopital's rule or you may not use any unproven rules. So right here, we will cover L'Hopital's rule. And from now on, you can use it unless you're told you can't. And there is a good chance on the final you'll be told you can't for certain problems, you can for others. Now, L'Hopital's rule is a useful rule for computing certain limits. Many limits we've seen. And it combines results on limits with results on derivatives. So before now, well, before a couple weeks ago, we didn't have derivatives, so we couldn't have L'Hopital's rule. Although some students who have seen calculus before tried using it and lost points. So let's talk about this rule. If direct substitution for the limit of a quotient, so we have the limit of a quotient, it could be limit as x goes to infinity, or it could be limit as x goes to a number. I'll just say, to ease the notation, limit as x goes to a. But bear in mind, this could be a limit to infinity. If direct substitution gives 0 over 0, or a positive or negative infinity over a positive or negative infinity, then the limit of that quotient is given by the limit of the derivative of the numerator divided by the derivative of the denominator. Notice here, we're not taking a quotient rule. All we're doing is taking the derivative of the top and dividing it by the derivative of the bottom. So let's see a few examples. Example. Compute this limit. So we're back to computing limits, but now we can use some derivative rules or derivative results to compute limits. So let's see how this goes. Now, when we tell you, we meaning people who teach math, when we tell you not to use L'Hopital's rule, it is actually because we want you to be able to see how it works without it. In some sense, using L'Hopital's rule is a very large shortcut that, that in using it will cause you to jump over certain things that are important to see in limit computations in math. So right here, compute this limit. You may use L'Hopital. You don't have to. Yeah, I think you don't have to on this one. I think they factor. But compute this limit. So again, with computing limits, the first instinct is to try substituting and hope it works. Substitute, you get 16 minus 12 minus 4 over 16 minus 8 minus 8. So that's a 0 over 0. So here, I'm going to use L'Hopital's rule because we have something in the form 0 over 0. So here we're going to use L'Hopital's rule. And when we use it, each time we use it, I'm going to say that the equal sign is by L'Hopital's rule. And I'm going to do that by putting a little h over the equal sign to signify that we've used L'Hopital's rule. You could say h and then you could write 0 over 0. I'm just going to write h. And how do we apply this rule? Well, that limit equals this limit. How did we get that limit? Well, we didn't do a quotient rule. All we did was take the derivative of the top and put it over the derivative of the bottom. Derivative of the top, 2x minus 3. Derivative of the bottom, 2x minus 2. And now, again, you try to substitute and you see if that works. In this case, it will work. because you get 8 minus 3 over 8 minus 2, which is what? 5/6. So we did this limit without having to factor because now we have some derivative results. Let's do another. Notice we did not use the quotient rule for the derivative. We just did the derivative on top over the derivative on the bottom. No quotient rules yet. You might see a quotient rule for some of these eventually. Well, we might see a quotient rule show up in some of these eventually. When we covered squeeze theorem, we showed that this limit is 1 using a graph and a squeeze theorem argument. But here, we could use L'Hopital's rule to find this limit as well. Why can we use L'Hopital's rule? Well, good ordered pair labeling. Sine of 0 is 0. You try a direct substitution here, you get 0 over 0. When you have 0 over 0, you can apply L'Hopital's rule. So equals by L'Hopital's rule, the limit as x goes to 0, derivative of sine is cosine. Derivative of x is 1, so we have cosine x over 1. That's, of course, just cosine x. Cosine of 0 is 1, so we can do a direct substitution. We get 1 over 1, which is 1. So this limit is 1. You could use the squeeze theorem to show it. That took probably 15 minutes of a video to go through that argument. Or you could now use L'Hopital's rule and do it in 2 or 3 steps. Let's do this one. E to the x minus 1 over x squared. So you try substituting here. What happens when you substitute here? You get e to the 0 minus 1 over 0. E to the 0 is 1, so you get 0 over 0. When you have 0 over 0, you can apply L'Hopital's rule. So by L'Hopital's rule, limit over here equals this limit I'm about to write. Derivative of the bottom is just 2x. Derivative of the top is e to the x minus 1 minus 0. So e to the x minus 1. And now we have a new limit, so let's try substituting over here. Let's try substitute. What happens if we substitute here? E to the 0 minus 1 over 0. 1 minus 1 over 0. So again, you get a 0 over 0. What do we do when we have a 0 over 0? Well, you could try factoring or multiplying or something. Or you could use L'Hopital's rule a second time. We will now apply L'Hopital's rule to this limit because, again, we had a 0 over 0. Over here, we had a 0 over 0. We could apply it over here. It's a new limit. We could again apply L'Hopital's rule. That's a 0. We still haven't taken a limit, so we still have to write that the next thing we get is a limit. Limit as x goes to 0. The derivative of the top is e to the x. The derivative of the bottom is 2. So now, again, we hope we can substitute. In this case, we can. And we just get 1/2. So you could apply L'Hopital's rule more than once to the same original problem. You could apply it like 6 or 7 times if you have to. Let's do another example. Compute this limit. Limit as x goes to infinity of what? E to the 5x over x squared. So here, when we mean substitute infinity, it does mean take the limit on the top as x goes to infinity, substitute, or not, and then the limit on the bottom as x goes to infinity, not a direct substitution, because we can't directly substitute infinity. But again, we're saying upon direct substitution, upon taking that limit as x goes to infinity, if the fraction is of a certain form. What form does this fraction take? Well, e to the 5x, the graph of e to the 5x looks like that. So as x goes to, it looks something like that. So as x goes to infinity, e to the 5x goes also to infinity. On the bottom, that's an infinity, on the bottom, as x goes to infinity, x squared goes also to infinity. So this limit here takes the form of a positive infinity over an infinity. And now we can apply L'Hopital's rule, because L'Hopital's rule applies to limits that take the form infinity over infinity. So that first limit equals this second limit. Derivative on the top, using chain rule, is e to the 5x times 5. Derivative of the bottom is 2x. Well, that's great. What do we have now? Well, again, we try a substitution. On the top, we're again going to get an infinity, because it's just going to be a 5 times infinity. On the bottom, we're going to get an infinity. 2 times something that goes to infinity will go to infinity. So again, we have an infinity over infinity. When we have an infinity over infinity, we can apply L'Hopital's rule. The derivative on the bottom is just 2. What's the derivative on top? Well, the derivative of e to the 5x is 5e to the 5x, using the chain rule, 5e to the 5x. So we have 5 times 5e to the 5x. 5 times 5e to the 5x, 25e to the 5x. And to compute this limit, well, again, you let x go to infinity. What happens? As x goes to infinity, the denominator goes to 2. The top goes to 25 times something that goes to infinity. 25 times something that goes to infinity is infinity. Infinity divided into 2 pieces, still infinity. So this limit is infinity. Here, we're going to see how we can use L'Hopital's rule on limits that don't necessarily look like they take the form of a 0 over 0 or an infinity over infinity, but they actually can look like that. So L'Hopital's rule, part 2. Recall these 2 limits. Limit as x goes to infinity, 1 over x equals 0, and as x goes to 0 from the right, 1 over x goes to infinity. And we use the graphs to see that. As x goes to infinity, that function goes to 0. As x goes to 0 on the right, that function goes up to infinity. Now, through, quote, substitution. So right here, we can't actually divide by 0, but we can use these graphs, or divide by infinity. We could use these graphs to observe algebraic structures. And these algebraic structures are all in quotes because they're not actually equal. They are equal in the sense that we can think of them as acting like this, but they are not equal. So we can see the algebraic expressions here. 1 over infinity acts like 0. Here, 1 over 0, on the right of 0, acts like infinity. And we're going to use those 2 observations, 1 over infinity acting like 0 and 1 over 0 acting like infinity, to help us manipulate symbols so that we can apply L'Hopital's rule. So observe. We can use this kind of symbol manipulation on expressions of the form 0 times infinity. And we can manipulate the symbols in this way. Now, 0 times infinity is not a form on which we can apply L'Hopital's rule. We need an infinity over infinity or a 0 over 0. But what we can do this is a colon here, not another multiplication. What we can do to a 0 times an infinity, 0 over here acts like 1 times infinity. So I'm going to put all this in quotes, quote. So this quote equals 1 over infinity times infinity by this symbol manipulation here. Infinity, or 0 times infinity, behaves like a 1 over infinity times an infinity. And of course, 1 over infinity times an infinity looks like an infinity over infinity. So if we have something and we substitute and get a 0 times infinity, we can actually rewrite that as an infinity over an infinity and then apply L'Hopital's rule. So let's look at an example. So here we have the limit as x goes to 0 on the right of 0 of x times log x. Again, we will try a direct substitution. Direct substitution gives us 0 log 0. What is log 0? Well, it's not a number, but as x approaches 0 on the right, remember the log graph. Log graph looks like that. As x goes to 0 on the right, log of 0 or log of x goes to negative infinity. So we have a 0 times a negative infinity. 0 times negative infinity, it's not immediate that we can apply L'Hopital's rule to that. But remember what we can do with that 0. We can rewrite this 0 as a 1 over infinity. 1 over infinity times a negative infinity. And then it's an infinity over infinity. How can we take this expression and write it as a 1 over infinity times a negative infinity? Limit as x approaches 0 on the right. Well, we're taking this x and we're throwing it in the denominator. How can we do that? Well, here's one way we can do it. Well, that's just about the only way we can do it. 1 over x in the denominator is the same as x in a numerator. Why is that? Well, if you simplify this expression, you would do log x divided by 1 over x. Log x is the same as log x divided by 1 over x is the same as log x times the reciprocal of 1 over x. So that reduces to log x times x over 1. Log x times x over 1 is this. So what we did was turn this 0 in the numerator into a 1 over infinity. Or turned it into an infinity in the denominator, I guess I should say. What happens as x goes to 0 here? Well, as x goes to 0, we again get what we expect. We have a negative infinity on top and an infinity on the bottom. 1 divided by 0 behaves like an infinity on the right of 0. Now we have an infinity over infinity. Now we can apply L'Hopital's rule. So equals by L'Hopital's rule this limit. Limit as x goes to 0 from the right, or on the right. Derivative of log x, 1 over x. Derivative of 1 over x, I'm going to use the observation that the derivative of 1 over x is negative 1 over x squared. You could get that from negative x to the negative 2 and then simplifying it a little, but I'm just going to jump straight to negative 1 over x squared. Remember, I did say it was useful to jump from 1 over x to negative 1 over x squared. Well, how does this simplify? Let's just, before taking a limit, let's do some simplification. We still haven't taken a limit. 1 over x divided by negative 1 over x squared is the same as 1 over x times negative x squared over 1. So we have a negative. We have 2 x's on top and 1 x on the bottom. So we're left with 1 x on top. And as x goes to 0, as x goes to 0, negative x goes to 0. As x goes to 0 on the right, I should say. So this limit is 0. let's look at another example. So in that first example, we took a 0 over 0, or we took a 0 times infinity and turned it into an infinity over infinity. How about this example? Limit as x goes to 0 on the right of x cotangent x. Well, again, we try substituting. You get 0 times cotangent of 0. What's cotangent of 0? Cotangent of 0 is cosine of 0 over sine of 0. What are cosine and sine of 0? Cosine of 0 is 1. Sine of 0 is 0. We're on the right of 0, so the trig functions are all positive. So that 1 over 0 will behave like a positive infinity. So here, through substitution, we have an expression that looks like a 0 times an infinity. Well, how are we going to deal with that? We're going to deal with that by turning the 0 into a 1 over infinity. And we're going to do that the same way we did the first one. We haven't taken a limit yet. We haven't applied L'Hopital's rule yet. But we're going to take that x and throw it in the denominator. Writing it like this would be incorrect. This is a different expression. And it's still it's an infinity over a 0, and you can't apply L'Hopital's rule to that. Writing it like this is correct, because this is actually the same expression as this one, through multiplying by the reciprocal of the denominator. Well, now we have an infinity over infinity, so we can apply L'Hopital's rule. Derivative of cotangent. What's derivative of cotangent? Negative cosecant squared. Derivative of 1 over x, negative 1 over x squared. We have a negative on the top and the bottom. Just get rid of them. And now what do we have? How do we take this line? This has too many fractions in it. So let's get rid of some of those fractions. Limit as x goes to 0. We could write this as x squared cosecant x, or x squared cosecant squared of x, but I don't like cosecant all that much. What we can do, cosecant is 1 over sine. So here, this limit now equals the limit as x goes to infinity of x squared, that goes in the top, over sine squared, because cosecant is 1 over sine. Well, still, this doesn't look completely obvious. You could substitute, get 0 over 0, apply L'Hopital's rule. You'd have to apply it twice in this case, if you don't make this next observation. X and sine x are squared. So you can take that square out, and now you have just the limit as x goes to infinity of x over sine x squared, which equals, I said infinity, I meant 0 on the right. We can throw limits inside squares. We have the result that limits go inside compositions. Compositions. We know how to take the limit on the inside of that square. Sine x over x as x goes to 0 is 1. The reciprocal of 1 is 1. 1 squared is 1. You could also apply L'Hopital's rule on the inside to get 1 over cosine x, but in the previous video we did the limit of sine x over x, so we just took the reciprocal of 1. So with these 0 times infinities, there is a good bit of simplification that you might have to do. The ones on the worksheet and the homework, there isn't as much simplification as one like this, but there is still a little. The last limits we'll take using L'Hopital's rule have the form 1 to the infinity infinity to the 0 or 0 to the 0. And what we're going to do is introduce a natural logarithm to an expression that takes this form, and then we will turn it into a limit on which we can apply L'Hopital's rule. And what would that look like? I'll just show what it looks like for one of these. So to compute a limit that takes the form 1 to the infinity, let's throw a natural log on it. And let's put this in quotes because we're doing symbol manipulation, not true equals. Well, if we have something log of 1 to the infinity, well, that's the same as infinity log 1. What's log 1? Well, this point is 1, 0. So log of 1 is 0, or you could have said e to the 0 is 1. So this is actually an infinity, well, this is actually now something that takes the form 1 to the infinity by throwing a log on it can now be turned into an infinity times 0. And we already saw in the previous examples how we can handle an infinity times 0. We can turn that into an infinity times a 1 over infinity, which is an infinity over infinity, and then we can apply L'Hopital's rule. And the other two are similar. The other two, well, this would become 0 log infinity, 0 times infinity, and then infinity times 1 over infinity. Well, I guess I should say 1 over infinity times infinity. This one, 0 log 0, 0 times negative infinity, and then 1 over infinity times times negative infinity, and then apply L'Hopital's rule. So let's look at a couple examples of how this would work. Let's compute this limit. Compute x to the x. We used the logarithm before to take the derivative of x to the x. Let's now take the limit as x approaches 0 on the right. These zeros on the right are because natural logarithm is not defined on the left of 0, so we need to stay on the right of 0. Well, x to the x. As x goes to 0, this goes to 0 over 0. So that is the third one we wrote. This is a 0 to the 0. So what we're going to do is compute a different limit. So we'll say we compute the limit as x approaches 0 on the right of log of x to the x. We're not yet computing this limit on top. We're computing the limit of this with a logarithm on it. If we throw a logarithm on something, that is a new limit. So this is all technically side work. But we can get rid of that exponent using a logarithm rule. This is now x log x. As x goes to 0, this takes the form 0 times negative infinity. So what we're going to do is throw that 0 in the denominator. We actually saw this limit a few minutes ago, but let's do it again. We're going to throw the limit in the denominator, or throw the x in the denominator as a 1 over x. These expressions are equal through multiplication by the reciprocal of the denominator. Now we have an infinity over an infinity. Once we have an infinity over an infinity, we can apply L'Hopital's rule. Derivative on top is 1 over x. Derivative on the bottom is negative 1 over x squared. Simplify that fraction a little. Limit as x goes to 0 on the right of negative x, because the negative stays there, and then x squared over x is just x, and this limit is 0. Well, that's great. We just found that that limit is 0. That's not the limit we wanted. We just computed a limit we didn't want. But we can use this answer to find the limit we want all we have to do is remove this logarithm. If we remove the logarithm, then the limit we found is the limit we want. How do we remove a logarithm? How do you remove that 2? You invert the 2. How do you invert a logarithm? You throw an exponential on it. So the limit we want is this limit without that logarithm. So we take e to get rid of the logarithm. You take e to every one of these things. E to this thing, e to that thing, and they're all equal. But the answer we want, e to the 0, and e to the 0 is 1. So this limit equals 1. And to compute that limit, we did a separate limit. Let's do, what did we do? We did a 0 to the 0. Let's do this one. Let's do this limit, what's this one? This one's a 1 to the infinity. So limit as x approaches 1, this time on the right, of x to the 1 over 1 minus x. So right here, you let x, I'm looking for a certain example. Maybe I don't have it written down. Okay. Right here, you let x equal 1. What do you get? You get 1 to the 1 over 1 minus 1. That's a lot of 1s. But that's 1 over 1 to the, or 1 to the 1 over 0, which behaves like a 1 to the infinity. When you have a 1 to the infinity, you can turn it into something on which L'Hopital's rule applies by throwing a logarithm on it. So let's do that. So as side work, we compute limit as x approaches 1 on the right of the logarithm of this. The logarithm of that, just bring that 1 over 1 minus x out front. What is this limit? Well, this expression here, the 1 over 1 minus x as x goes to 1, that is an infinity. It's a positive infinity. This here is a negative infinity. Sorry, this here as x goes to 1 is 0. So here we have a negative infinity, a positive infinity times a 0. Well, we can turn that into something on which L'Hopital's rule applies. Here, if we just write this as one fraction, it actually does it for us. We've been turning these into infinity over infinities, but we can actually just turn this one into a 0 over 0. Those expressions where I went from 0 times infinity to infinity over infinity, you could also turn them into 0 over 0 and apply L'Hopital's rule. We'll do that here. Limit as x goes to 1 on the right now equals this limit. As x approaches 1, what do we get here? We get a 0 on top, log of 1 is 0, and we get a 0 on the bottom. We can apply L'Hopital's rule. Equals, using L'Hopital's rule, this limit. 1 over x is the derivative on top. Negative 1 is the derivative on the bottom. This simplifies to just negative 1 over x. And as x goes to 1 on the right of 1, this goes to negative 1 over 1, which equals negative 1. Well, that's great. We did all that work, but that did not give us the answer we want. Negative 1 is incorrect, because we want this limit up here. We don't want this limit. We're using this limit to find that limit. And we take e to everything down here, which gives our answer as e to the negative 1. So these L'Hopital's rule, there are a lot of different forms these could take. Try the ones on the worksheet, or try the one, however many I put on the worksheet. This process does take a little getting used to, throwing a logarithm on it and then applying L'Hopital's rule. But it is a useful thing to go through, so see how they go.